Okay, it's a great honor. It's really a great honor to have opening talk of a very special event. To me, it's celebration of Viktor Matveyevich Buchstaber, remarkable mathematician. And I have known Viktor Matveyevich actually all my scientific life, still since I became a student of Sergei Petrovich Novikov. This is the photo of 2015 with Viktor Matveyevich, Sergei Petrovich, Igor Krichever, and Boris Dubrovin. And I must say that I was the first student of Sergei Petrovich Novikov who did not start with algebraic topology. All the previous generation, of course, starting with Viktor Matveyevich Buchstaber, had a very important contribution to algebraic topology. So I started in mathematical physics, which is also topic of the conference, and more precisely integrable system or soliton theory. But I always but the seminar of Sergei Petrovich Novikov was a mixture of talks in soliton theory, on solitons, and on algebraic topology. And I remember Viktor Matveyevich very well giving talks on algebraic topology. But I must say that I do not consider myself expert in algebraic topology. In fact, everything what I learned in algebraic topology was from Viktor Matveyevich. And the most important probably was our visit to Maryland. We visited Sergei Petrovich Novikov for a month, and we were staying in Seven Springs Village, and the last bus to Seven Springs Village was at 6 o'clock, so we have a very long evening, and that was a lot of discussion, and that's where during this month I learned about algebraic topology a lot. And it led eventually to our first paper, which I like very much, where the methods of integrable system were applied to topology. So, I'm going to talk about later work, mostly recent work, where we have where you will see algebraic topology, more precisely complex cobordisms, combinatorics of polyhedra, and mathematical physics, all this area which is where Viktor Matveyevich made substantial contribution. So this is another photo from 2008, and you see I'm struggling with topology, and Viktor Matveyevich knows the answers, right? Anyway, so that was, by the way, celebration of Viktor Matveyevich, I think, 65th birthday, right? It was very, very important event. Anyway, I'm going to talk about later work, and maybe I will go straight to the theorem of Milner and Novikov. So we're talking about complex cobordism, and bordism and cobordism. They defined in the category of U manifold, and U manifold manifold with stable complex structure means that you consider a tangent bundle of up to addition of trivial, and the stable complex structure is complex structure introduced in such a direct sum, chosen one. Of course, if you have complex manifold, then it's you have a natural U structure. But in general, the theory of complex cobordism and bordism were developed by Milner and Novikov in 1960s, and the structure is remarkably simple. So, namely, complex cobordism ring is actually polynomial ring Z of variable in every dimension, in every even dimension. Well, actually, it should be for cobordism, the degree of the generator should be negative, and you have two closed U manifolds are Bordant if and only if the corresponding Chern numbers are the same. So because of the complex structure in the stable tangent bundle, Chern numbers are well defined, and they characterize actually completely manifold. The main problem is, what can you say this about Chern numbers? What are the restrictions on the numbers to be Chern numbers? Anyway, so this is actually the first page of seminal paper by Viktor Matveyevich Buchstaber. I'm actually turning to this paper again and again because it's really seminal. I mean, there are so many important things there, right? So one of the things is, so this is called Chern-Dold character in cobordism, and maybe I will, because it's small, I will. There is one of the result of this paper. It's written there that it's explicit formula for the formal series, for the formal group of geometric cobordism, and this is just one of the results, which is really important one. So it is shown that you know, Chern-Dold character is in complex cobordism is uniquely defined by this section. U and beta of Z will appear. This is and it's just formal series, exponential formal series. You see Z plus B to N, and B to N were characterized completely in this paper of Viktor Matveyevich by a condition on normal characteristic Chern classes. So what we have realized is representative, but as I just mentioned, that this beta of Z, this series, is also exponential of the commutative formal group of geometric complex cobordism, which was introduced by Novikov, right? So it satisfies this property. Right. Now, as I mentioned in this paper, this group is explicitly described in terms of certain manifold, and but the question about exponential was open. All right. So, and Quillen actually made an important contribution by identifying this group with Lazar universal one-dimensional commutative formal group, which means that complex cobordism, in a way, they showed also significance of complex cobordism as extraordinary homology, right? I mean, it's because the corresponding group is actually universal. So logarithm of this group of geometric cobordism was known after Mishchenko. It's known as Mishchenko series, and it's beta minus 1. It's logarithm. Beta is exponential, And it has this, right? Look at this. I mean, it's CPN, but divided by n plus 1, not n plus 1 factorial. It's un plus 1 divided by n plus 1. And I think it's simplicity of this answer was a kind of misleading. And maybe that's why this observation, which I'm going to present now, which is our joint work with Viktor Matveevich, was not done until 50 years later, right? Because everything was ready essentially in 1970 when Viktor Matveevich wrote his paper. The answer, it turned out that as a representative, one can take a smooth theta divisor, right, of general principally polarized abelian variety. So you take general principally polarized abelian variety, you take theta divisor, it will be denoted as theta n, and this can be chosen as representative. Now, as I want to argue, this as an algebraic variety is quite complicated, right? I mean, it's not, it's far from being as simple as CPN, and but at the same time, it's very natural from the point of view of integrable system, where, and in particular, Novikov school, Dubrovin and Krichever, in particular, made a very significant contribution using theta function to solve important nonlinear equations. So theta functions and theta divisors are very natural from integrable system point of view, but as a choice of representative, it probably was quite unnatural at the time. That's why it was, I think. Now, why it is important? Because if you know this, then you can write down any cobordism class of any U manifold as a linear combination of product of theta divisors with coefficient being Chern classes of the normal bundle of M to N, right? I mean, this is the thing. So as a result, we have a new basis of in the ring over Q, for example. This is instead of CPN, we can use theta and their products. Okay, so this is the kind of first result, and now I'd like to explain very mysterious to me relation of theta divisors with permutohedra, right? But let me recall that if you consider principally polarized abelian variety, then it has canonical. Well, canonical. I shouldn't say canonical. Probably it comes with line bundle by definition with one-dimensional space of sections. And this is they generated by classical Riemann theta function, and the theta divisor is actually zeros of this. And old result of Andreotti and Meyer say that for generic principally polarized abelian variety, theta divisor is smooth, and it's algebraic variety of general type. That's easy, follows general type. So you have, you know, this kind of Fano, Calabiao, but this is general type. It's like from algebraic point of view, algebro-geometric point of view, it's complicated in a way. And the cobordism class doesn't depend on the choice of such abelian variety, so we can talk about theta divisor when we take algebra-geometrically they are different, but cobordism class are the same. So just example, theta 1 is smooth genus 2 curve. In fact, it's leaving every abelian two-dimensional varieties, Jacobi variety of genus 2 curve. And theta divisor is simply Abel embedding of this curve into this Jacobian, right? Jacobian variety. And so this is genus 2 curve, therefore, right? So it's kind of the first curve, if you want, of general type, right? I mean, Euler characteristic negative. And then theta 2 is symmetric square of non-hyperelliptic curve of genus 3. And then I don't think that you can say much about this. It's complicated apart from the definition, right? So now we want to compute some numerical characteristic, right? And for this, in particular, we can look at Hirzebruch genus, right? And Hirzebruch genus is defined by characteristic power series Q of Z. You can take any Q of Z, AN are arbitrary, for example, over Q, for example, and then you define phi. I have written this as integral, where Q of Ti are Chern roots, so-called. Because the right-hand side is symmetric, it can be expressed in terms of Chern classes, and therefore it's a form, and you can integrate. Or you can simply so this is Hirzebruch genus, and you can choose any Q. And then you have some numerical characteristic in this way, right? But a remarkable discovery of Hirzebruch is this chi Y genus, and this is a very, very special Q of Z written here. And so for in particular, chi 0 is third class, which is the motivation for Hirzebruch was to understand the topological meaning of what was called arithmetic genus, right? And he realized that one can view this as Hirzebruch genus in this case, corresponding to this special function corresponding with y equal to 0. But then he realized that if one take other values of y, then you have Euler characteristic and signature. Now, this is our result, which explain the importance of theta divisors for in this theory, right? So you can view it either way. So if you want to compute Hirzebruch genus of theta divisors, then it's simply you write down generating function, exponential generating function, and it turned out to be simply z divided by q of z. Very simple formula, right? So if you know q of z, you know phi of theta. But you can view it also the other way around. You can you may say that if you know Hirzebruch genus of theta divisor, then you know q of z. And this is just simply exponential generating function. And in particular, for y equal to 0, as I said, we have third genus, arithmetic genus with q of z to be is q of z is given, by the way, kind of Bernoulli numbers, yeah, I mean, Bernoulli numbers will appear, but because it's 1 over q of z, it's just 1 minus exponential, and therefore third genus of theta n is minus 1 to the n. And if you compare this with CPN, and this is a kind of logarithm CPN, and exponential is theta n, then third class of CPN, third genus is 1, right? Now, Euler characteristic is minus 1 to the n plus 1 factorial. So it's quite large Euler characteristic. But let me say a bit more about this signature. As I said, remarkable Hirzebruch result is that signature of M to N can be given as Hirzebruch genus with Q of Z being Z divided by Z quad Z, Z quad Z. Also Z divided by Q Z is tan. And this is expansion of tan, and tan is the expansion is again Bernoulli numbers. So Bernoulli numbers naturally appear as expansion of chord, but magically they also turned out to be coefficient of 1 over this, right? But you see, it's not just Bernoulli numbers, you have this coefficient, right? So as a result, we have signature in terms of the classical Bernoulli numbers. So Bernoulli numbers are defined by generating function, and they are quite mysterious numbers, right? So in that sense, signature being Bernoulli numbers is kind of indication that theta divisor are sophisticated object. Now, we can compute also from using Lefschetz hyperplane theorem, we can compute Betti numbers. By the way, it's not simply connected. Fundamental group of theta n coincides with fundamental group of abelian variety, which is a torus, 2n plus 2 dimensional real torus. And therefore it's a large abelian group, right? And Betti numbers are binomial coefficient, except the middle one, because you have Poincaré duality, and Lefschetz hyperplane theorem allows you to compute everything but the middle one. And the middle one you compute using Euler characteristic, which we know to be n plus 1 factorial. So, and it's interestingly enough, it's a sum of n factorial and Catalan number. So this is the kind of thing you see. This what puzzled me. So multiplication in this cohomology group, by the way, we don't understand. Well, I don't think that it is known, right? We didn't find with Viktor Matveevich any traces of studying this. Cohomology were studied, Betti numbers were known essentially, but multiplicative structure is I think unknown, a very interesting question. And you see Bn of theta n middle is n plus 1 factorial plus Catalan number, and signature is Bernoulli number. I think this combination shows that there is something very tricky going on here. So now, now I want to explain a mysterious relation with permutohedra, because I mean originally, so what we showed? We showed that exponential of this formal group of the formal group of geometric cobordism is actually exponential generating function of theta divisors, right? And logarithm is kind of normal, well, if you n plus 1 of CPN, right? So logarithm is complex projective spaces. Exponential is theta divisor. This is a kind of one duality, right? And what you see here, I mean, on the level of polyhedron, CPN is simplex. But then at some point, we realized that there is a mysterious relation with permutohedron. Permutohedron is you know, one of the famous, in fact, Viktor Matveevich had several remarkable papers about studying of about series of related to permutohedra and associahedra, and but this is a very natural object. This is convex hull of the point, and which are permutation of a vector. So we choose rho here, 1, 2, and n plus 1. So we live in an n plus 1 dimension, but this convex hull is n-dimensional. So it will be n-dimensional. So these are the first. The second one is hexagon, and this is permutohedron. And as you see here, you have squares and hexagon, the structure, right? We will be interested essentially in combinatorics of this, which is very well studied, right? I want to show only what is new. What is new is mysterious relation with theta divisor, right? So what is, let me say a few words for Nikolai Petrovich, maybe that permutohedron is, of course, is Voronoi cell. It's Voronoi cell of dual to the root lattice an, which is also kind of famous lattice in the covering. But I want, so on the left actually it's written what is Voronoi cell. If you take points which are closer to a particular elements of the lattice, then you will have this Voronoi cell, and the Voronoi cell of hexagonal lattice is is hexagon, which is exactly permutohedron. On the right, it's usual, then it's square, right? So it is known that it has maximal number of facets, which is faces of codimension 1, right? It's 2 to the power n plus 1 minus 2. Also these are extremal cases. So there is a notion of graph associahedra. I don't know who was the first to introduce it. There are several, I think, people. It goes back, I think, to De Concini and Procesi, wonderful compactification and algebraic. But then Divisors, I think, Fomin, Zelevinsky, I think, considered this. Anyway, so there is a notion, graph associahedra. To any graph, there is a polytope, right? And if you consider two extremal cases, one, if you consider just disjoint set, no edges at all, then you have simplex. And if you consider complete graph, so all possible edges, then you will get permutohedron. So associahedron in the middle, it corresponds to the AN type of diagram, right? Path type graph, right? So therefore, if we think of delta n simplex as CPN, right? So you may say that the most complicated maybe is, well, this is a kind of explanation I have in mind about this duality, but this is all vague, right? So talking about combinatorics, right? As I said, the number of combinatorics of permutohedron is very well studied, and a lot of classical numbers hidden inside of permutohedron. Permutohedron, in general, polytopes actually are very, very complicated objects compared to manifolds, simply because it's combinatorics, right? I mean, of course, it's the way how you look at. But anyway, so combinatorics co-dimension K faces are given by essentially by Stirling number of second kind. So combinatorially, they defined as partitions of set 1n into k parts. Okay, so for example, these are f polynomials so you have S is segment, right? I mean, it's let's pi 2 is hexagon, as you remember. So this is written that S square, for example, it's hexagon. 6 is 6 edges and 6 vertices, and this is for and 14 is, you see, it's 16 minus 2. It's a maximum number anyway. So these Stirling numbers, they are known. And corresponding H polynomial is also classical. I mean, Stirling and Euler is all we're talking about 18th century, right? So they considered this and introduced this number, and they think. So it's called Eulerian polynomial, right? Eulerian polynomials, and A and K are Eulerian numbers, right? And they count something else. They count permutation in Sn with exactly K descent, A and K. So then you have t plus 1, and this is the thing, right? So this is H polynomial, and it has this symmetry because permutohedron is simple polynomial. You have this Poincare duality kind of for H, and it's not accidental because it is Poincare polynomial of corresponding toric variety, but I will mention maybe later. So this is the relation with theta. So what's the relation with theta? So first of all, if you have theta divisor, you can create more varieties, sub-varieties, by taking multiple intersection of these theta divisors. And they have actually, they play a special role in Hodge problem, Matuk theorem. Hodge conjecture was proved for abelian variety by Matuk, and he showed that this intersection generate all generate the ring of subvarieties of abelian variety. So what is the relation? The relation is that if you consider tot genus of theta n minus k, for some reason it's coincide up to a sign with the number of codimension k faces, right? So this is and the proof is just computational, basically. We compute left-hand side, right-hand side, and they're the same. So that's kind of observation came first, and then once it is done, you can check because you know left-hand side. I still think it's mysterious, so we don't have good explanation for this, right? Why it is this. Now, a bit more. So if you, let's consider the toric variety. So if we have this permutohedron, which is permutation of 1 to n, and permutohedral variety, and Poincare polynomial is essentially H polynomial. It's just double gradient, and then there is a duality relation, which is I'm still puzzled by them. So if you consider chi y genus, which is the most important probably genus among Hirzebruch, this is important from the theory of formal groups and from the topological interpretation, algebro-geometric application. So then they are essentially the same, right? They different only by sign, right? And in particular, well, this is a corollary already. The Betti number is actually chi k, which is generalization of Toda genus. Right? In fact, we had a conjecture that they simply this is true at the level of cobordism classes, but the computation done by student of Viktor Matveevich Misha Kornev showed that for n equal to 3, it's not true. It's x permutohedral variety is not. But that makes this relation even y chi y genus behaves like this, right? So it's like mirror symmetry. It's not. It's some numerical characteristic. I think. Now, so a little bit of mathematical physics and integrable systems, right? So there is one of the most important integrable finite dimensional system is finite Toda lattice. If you have n plus 1 particles on the line, exponential interaction between neighbors, qr, qj minus qj plus 1, and you can introduce Flaschke variable, and then equation of motion, nice algebraic form, right-hand side is quadratic in B. And early observation of 1974 say that it can be written in Lux form or simply L dot equal to BL, so which is actually the same as isospectral deformation, because every isospectral deformation can be written in this form. So this shows that matrix L, spectrum of matrix L is preserved from this, and spectrum means that so which gives you n integral which can be shown in involution. So it's integrable system in Liouville sense, right? So let's fix the integrals, right? Let's fix the integrals. So A and B entries of L, they are A is momenta and B is expressed in this. Let's fix integral, for example, right? I mean, it's anyway spectrum by fixing spectrum. It depends on lambda, but generically right. So so what you would expect in general, if you fix integral in integrable system, you would expect torus. That's Arnold-Liouville theorem. Fix the integral, you have torus. So from this point of view, integrable systems are boring. It's a story about fibration of tori. Well, I remember because I met Carlos Tomei at the time, and he told me about this paper, which I missed. I met him in the 90s, and he said that, by the way, and he told me about this. I said, wow, I mean, how come instead of torus, you have very highly non-trivial manifold with Euler characteristic, which you have already seen. And this is, again, observation, which is just observation, right? Which we made with Viktor Matveevich, that for some reason Euler characteristic of Tomei manifold is coincide with signature of theta divisor. No, and this and bk of M2n is b2k of permutohedral variety. That's more or less follows from later theory. But the thing with permutohedra is it was already in Tomei paper. This is the picture, by the way, from his paper, which is a remarkable paper. It's interesting because he said that this is the first time people usually using gradient flows in Morse theory to study topology, I will be using Hamiltonian flows, because Toda system, remember that this is a Hamiltonian flow. And but I will be using this in the same way like Morse using this in Morse theory. So this is how he found Euler characteristic by studying simply fixed point of Toda flow. Everything is. The irony is that this is actually gradient flow. it is gradient flow, but this is non-trivial observation. In fact, Moser mentioned this, but that was kind of strange gradient interpretation. It turned out to be that there are more natural gradient interpretation. So essentially, we can say that Tomei, without understanding this, he was using Morse theory to study this, but he used, instead of gradient flow, he used Toda flow. And Toda flow is integrable, so you can solve everything, right, explicitly, right? So now I want to just tell this story of Steenrod cycle realization problem. So this is the problem. There will be a talk, I think, about this problem by Rождественский, I think. Anyway, so if you have, so when you have a cycle, k-cycle, inside topological space, we would like to think of this as image of some manifold. How wrong is this? So Tom said that up to multiple, it's yes. So it means that you can multiply cycle by some number, and it will be realized as an image by of some manifold, right? And then the question is, which is there yk manifold which can realize any cycle, right? So for example, sphere, for this yk should be complicated enough, because if you consider genus 2 curve, and if you have cycle, fundamental cycle, you cannot realize it by mapping sphere, for example, right? It should be at least 2. And this is remarkable result of Sasha Gaifurin. Really, when I learned this, it's kind of 2 surprises. First was Tomei manifold, which is kind of showed what Tomei said, that contrary on what we think that integral level is torus, we have very complicated manifold. And then Sasha said that actually it is the most complicated manifold in the sense that you can realize any cycle by using some covering of this. It's remember that for n equal to 2, it's genus 2, and by considering covering, you can get any genus G surfaces, right? Okay, so this is remarkable. I must say that, so you're not confused. Of course, there is nothing wrong with Arnold-Liouville theorem, right? Arnold claiming that if you have symplectic manifolds, right, and then you have some condition, then it must be torus. Now this is Poisson manifold, so there is a degeneracy. Because of this, it's not quite. Arnold-Liouville in this case will be Rn, will be open set of Toda, right? So Arnold simply said that in this case that there is an open set which is open, but you know, any manifold can be glued out of Rn. So in this case, for open Toda, Arnold-Liouville torus is simply cell, one cell of this. So no contradiction, the way it's glued. But nevertheless, it's true that if you fix integral in this Poisson manifold, you have the most complicated thing. Now, there were 2 important developments. Bloch-Flash-Conrad-Hue found a natural gradient interpretation of Toda flow on Tomei manifold. So in that sense, it became clear that what Tomei did after Bloch-Flash-Conrad-Hue, what he did is just more theory, But nevertheless, full credit to Carlos Tomei, because it was 1984. I mean, we all missed an integrable system. I think most of us, at least, until. Tomei result was noticed by topologists. Fried, I think, first completed calculation of, and then Davis and Januszkiewicz, which was also considered a development, substantial development in the work of Viktor Matveevich and his school, right? So just to finish, so this is references, which is the most important. This which is reference to Carlos Tomei and to papers. And let me finish with wishing Viktor Matveevich many happy returns. And it was, Viktor Matveevich, a great pleasure to work with you. And I hope that we will continue to do this. It's really a pleasure. Every minute I enjoy our work together.
Yes, thank you very much. And are there any questions, comments?
Well, I've got two small questions. First one, when you consider this theta divisor,
yes,
you showed beta numbers.
Yes.
But is there any torsion in homology?
No torsion. No torsion.
Yeah. And the second question is about the very first formula. These C lambdas.
Sorry, very first formula, which one?
There was C lambda mu.
Yes.
This
Yes.
the lower formula. Is this corresponds to monomial or to elementary polynomials?
You're absolutely right. I mean, this is something which actually I learned from Viktor Matveevich, and I was puzzled because you know, when you define Chern classes, right? Chern numbers, you use special basis. And Viktor Matveevich from the beginning said that monomial, and I couldn't understand why. Now I think it's deep, it's very clever. And it's already actually, I asked Viktor Matveevich who was the first, because to me, maybe I would use powers or whatever. I mean, there are many bases in symmetric function, but already in the first paper, what 1970, they use monomial symmetric function. So, and this is, I think, significant. To me, it's not obvious, but that was understood probably at some early stage, why one should use monomial. I think it's deep. To me, I'm still, it's magic to me. Magic done by, you know, Viktor Matveevich. But maybe he knows simple explanation, I don't know. Yeah, you're right. It's very important, monomial.
These are normal numbers, right?
This is normal. Normal and monomial.
Normal monomial.
Two things. Normal is natural kind of thing, but monomial is not obvious to me. And it worked with monomial, exactly with monomial. Well, I mean, there are, of course, reasons. Monomial are special, but why exactly them?
More questions? Maybe I have one. And over the last slides, I think that complex Tomei manifolds, which is also was mentioned by Davis and Januszkiewicz as a quasi-toric or whatever. Yeah, it also features here. I think it's
Yes, yeah. Well, I mean, I skipped this because I was very all the time. But in the last the last paper, theta divisor and permutohedra, we discuss also a Hermitian version, which is Hessenberg manifold, right. And I mean, it's we discussed this briefly as well, but I didn't have time.
But does it have meaning in the integral systems as well?
That's interesting, because the paper, there is a paper by Flashka, Ratiu, another paper, which not the one I mentioned, but the second paper, which I struggle to understand, because these people really came from integrable system, but what they're doing something not very natural to me, and so yeah, I mean, formally it's just complex Hermitian version of this. People from integrable systems studied this, but studied this from symplectic point of view.
So there is no like Hermitian version of the Toda flow or something like that?
Yeah, there is no attempt to explain why it is useful for application or what it is related to. They dealing with this already as an object in a kind of, you know, in symplectic geometry. Symplectic geometry. Right. So, but it is done by people doing integrable systems.
You showed me that paper, and Flashka and Ratiu. That's okay. Thank you. And
thank you for the lecture. I wanted to ask whether theta divisor can be seen as some kind of modular form.
Modular form?
Yeah.
No, to be honest, we were thinking of modular form, but not in relation with theta divisor.
I mean,
no.
there are like symmetries all over the place, so I thought probably you can be said it as such.
No. I don't know.
Okay, thank you.
all right, maybe we can postpone more questions until coffee break, which we're going to have. Now let's thank Aleksandr once again. And also a brief announcement. Tonight we'll have a reception party at the restaurant of Omega Sirius Hotel, which is nearby. We start from here after the last talk, or you can get there from the hotel if you'd like. It's about 40 minutes between the last talk and the reception. And also, we ask you to pay a contribution for this reception, so it's 2,000.